I'm Carly McAvoy, and we're doing homework 7B. 7B is talking about confidence intervals like we've been doing, but the confidence intervals we did initially were for proportions with z values, and we can do means with z values, and then also we did t value problems, and now we're doing, well, let me show you something. We could do this. We can find out an interval. I'm just going to put a box that is talking about the proportion of the population, and we found something like that. We can do something that's talking about the mean of the population, and we can also do something that's talking about the standard deviation of the population. So when we're doing something like this, we look at p hat minus the error, or p hat plus the error, right? When we're doing mu, we look at the mean for the sample minus the margin of error, and we look at the mean plus the margin of error for the mu. So those were pretty similar. For standard deviation, it's a little different. It's a different formula that we're going to use on either side. But it's the same idea. We're finding a confidence interval and using that interval to predict the population standard deviation. So because we don't know the standard deviation to start with, we're going to be using this S, which is the sample standard deviation, right? We're going to use S to help us find that. And so you can see that that's given in this problem. We still need to know the sample size because we're not given that population standard deviation. It's sort of like thinking about those t values, only we're talking about t values as the sum of squares around the mean, and so we use a table called the chi-square critical values. So we had critical value z, where when we knew what the population standard deviation was, we had critical values t when we didn't know what the standard deviation was for the population. And now we have these chi-square values, and the chi-square looks like that. It's sort of like a capital X. It's actually a little skinnier. And then we have a left and a right value. So we have chi-squared left and chi-squared right that we're going to be looking for. The degrees of freedom is the same that we've been doing, and that is n minus 1, which in this case is 20, because we had 21 minus 1. So our degrees of freedom are just going to be the same. And we're still talking about degrees of freedom because this is actually related to those t values, so we still have that. And then we want to find that to the right and to the left. It's a little different when we're talking about chi-squared because we're talking about the area to the right. So if I look at it this way, let me do two drawings. First of all, I know that it gives me the confidence level, which was 95%. So if I take 1 minus 0.95, I get 0.05, right? And so if I divide that by 2, because we're talking about the area in two tails, I get 0.025. That number shouldn't be different. What's different, should be different to you, is we're talking about the area to the right of that when we talk about the chi-square table. So in this case over here, where I have 0.025, what I have to the right of that is 0.975. That's just 1 minus 0.025. So I have 0.975 to the right. And over here, I have the 0.025 to the right. So that gives me two different values for my critical values. So I want to find those using the chi-squared table. I know a couple of things that I need to know. I know that I have 20 degrees of freedom, and I know for the left one, this is the one on the left, you can see this is left and this is right, right? For the left one, I have area of 0.975 to the right. And for the right one, I have an area of 0.025 to the right, so that's going to give my two different values. So if I look at my chi-squared table, which is available to you on the computer, I'm looking at a degrees of freedom of 20, and then I go over to 0.975 up here at the top. It's hard to read. Hopefully it'll be better on yours. And if I come straight down, I get 9.591 for my left value. That's 9.591. 20 degrees of freedom over here to the right to 0.025. That's what I had to the right. If I come straight down there, I get 34.170. So I have 34.10170. So if I was to look at it this way, I'm looking at 95% gives me two different values to the left and the right. You can see over here, I kind of drew that what I drew earlier. Now the confidence level is 95% here, and that's how I got that 0.95. They were giving us that. Now if I want to do a confidence interval, I'm going to use this formula right here. That is n minus 1 times s squared over chi-squared right, and then same thing, chi-squared left. Why would I put the right one over here on the left and the left one over here on the right? Well, when I do an interval like this, my smaller value should be on the left. And you can see that if I divide by a bigger number, I'm going to get a smaller answer. So that's why we want to put that over there. It gives us our smaller level, and that gives us our higher level. So we want to switch those and what you think might make sense. So if I plug in the numbers that I have here, 21 minus 1 is just 20. So you could just plug in your degrees of freedom straight there instead of doing that. And then our 0.28 squared, where did that come from? Well, that was given in the problem that s was 0.28. They give us the 0.28. So I put that in for my s into the second power. And then I have the chi-squared to the right, and that was the 34.170. And then the right-hand side, same thing on the top, and on the bottom I have my chi-squared on the left, which was 9.591. So you're going to put that into your calculator and do the calculations. That comes out to 0.214, 0.40. The actual problem asks for this to 2 decimal places. So rounded to 2 decimal places, it's 0.21 up to 0.40. So we're using that table to get the critical chi-squared value. Those are critical values. When we had critical z values, critical t values, now we have the critical chi-square values. And so those are the 3 answers that we're looking for, or the 4 answers. I don't know how many answers there were. This one was 9.591. This was 34.170. And when I plugged into that formula, I got 0.21 to 0.40. So those are the answers to that problem. And that's pretty much what all these problems are like. There's only 5 problems on this homework. And one of them is on your quiz, and that's this one, this number 1 type. So this is exactly what you have to do for your quiz, which means nothing more than that could show up on your test or your final. So this is all I'm going to expect out of the section 7.4, except that you have to still do the homework. So we're going to move on and take a look and see if there's anything of interest to talk about on these next pages. Okay, the next one, number 2, is asking you to do the same thing. It's that we have an n of 81. If n equals 81, then our degrees of freedom are 80, right? We have a 90% confidence level. 90% confidence level means I have 10% in the 2 areas, right? Because 1 minus 0.9 is 10% in the 2 areas. And if I divide that, I got 0.05. So if this is 0.05 over here, the area to the right would be 0.95. That's what I'm looking for that chi-squared left value. For my chi-squared right value, I have 0.05 to the right. So that's the area that I'm looking for my chi-squared right value. Okay. So looking at the table, and by the way, we know what our S is because it was given. We'll use that in a second. 18,876 is our standard deviation for the population. This one happens to be the salaries of college professors who took a geology course in college. Whatever. Okay, so about $69,000 is what they're looking at. Okay, so I'm going to go to this. My degrees of freedom is 80, and I'm looking at 0.95 for the left. So if I go down here to 80, and then I go to 0.95 on the top, you may not be able to see the top there, but it goes over to the fourth place. This looks to me like 60.391. It's really hard for me to read that. I think it's 60.391. Maybe you guys, your vision would allow you to read that. 60.391 looks pretty good. All right. When I did this problem earlier, I didn't get the exact same answer that the computer got. So we'll see if I do better this time. This was 60.391. To find my right value, I'm just going to go to that 0.05 mark. 0.05 is the second one in that kind of second half of the right half of that column. But I still go down to 80. 80. And what I get there, I'll lift it, is I get 101. I think it's 0.879. But that didn't get me exactly it. So I wasn't sure if it was maybe 379. Does that more look like a 3 or look like an 8? I'm going to go with 879 because that's what it looks like to me. And hopefully there's a tolerance built in. Okay, 879. Now I know my left and my right, and I'm going to use my formula to find those two values, and that is the square root of, it's n minus 1, and since our n is 80, it's just our degrees of freedoms, 81, so I'm going to do 80, times the, why did I squish it in there so closely? I don't know. Standard deviation of the sample to the second power, divided by the right-sided, because it's the bigger number, chi-squared. So I'm going to do 101.879. On the right-hand side, again, I have the 80, and I have the 18,876 squared. And on this side, I'm dividing by the left, which is 60.391. So those are the two values that I'm going to put into my calculator to get my two answers. So somewhere is my calculator. Here it is. You can see that I just put that one in already earlier. That one I did 379. I was trying to see like what's happening, but let's do this again. I have this. I have 80 times 18,876, and that value is squared. And then on the bottom, I have 101.879, and that gives me 17. See, look, 17 doesn't give me 17 anything. 16,727 rounded to the nearest dollar, and the answer they got is a little different than that, so I'm not sure what's happening there. But on the right-hand side, second function, square root, we have 80 times 18,876 squared over 60.391, and I get, if I round that, I get 21,725. And that is the answer they had. So how was I off on one side and not the other side? I don't know. But hopefully your numbers will work out better. It's the same process we did on number 1. The different thing I'm thinking about here is what area is to the right. So that's a little different with the left and the right thing. Other than that, we plug into those formulas that were given and we find that. That formula, again, is n minus 1 times s squared over chi squared on the right and n minus 1 s squared and then chi-squared on the left. So that's the formula that I plugged into that I gave you that one earlier. Okay, so I already threw away the answers, so maybe I wrote down the answer wrong, I don't know, but I tossed it into the bin. That was 7.4.9. Again, it's not going to be on your test. A chocolate chip cookie manufacturing company recorded the number of chocolate chips in a sample of 40 cookies. That's information I could use. That's in my degrees of freedom is going to be 39. The mean of their sample was 22.21. We're not going to use that to our calculations. The standard deviation is 2.93. We want a 98% confidence interval, which means we are taking 2% and splitting it amongst both sides, which means I have 1% on each side, right? And so if I look at my two chi-squared values over here, to the right of that would be 99% or 0.99. And for my other one, I'm looking at the 0.01 as given to the right of that for my chi-squared right. Now I want to go find those two values and use it to make my interval, right? And again, for my interval, I'm going to use that formula that I just gave you, n minus 1 s squared over chi-squared right and n minus 1 s squared chi-squared left, and I have to go find those two values before I can solve this problem. But I know this. I know that my degrees of freedom is 39. That's the n minus 1. I know s to be 2.93 squared, and so all I have left to find is that chi-squared value, and then I'm ready to plug into that. All right, so we can go find those if you'd like. The 39 degrees of freedom is not given exactly, just like with the t-values, it's so close that it's not a big deal. What was our 99.99? 40 is close enough. 0.99, 22.164. That's going to be my left one. 164. And my right one would be the 0.01, which is here. And I would come down to 40. And that's 63.591. More or less. Who can say for sure? And now I'm going to put that into my calculator. It's more of a calculation routine than anything else. 39 times 2.93 squared over 63.591. And I get about 2.29. That's not exactly what they had over there. Let's see what I get for the right hand side. I mean my answer that I wrote down. 39 times 2.93 squared over 22.164. And I get 3.87. 98% is 2%. 2% on each side is 1%, so 0.99 and 0.01. Yeah, that's how I get that. That's what I'm getting. All right, let's move on to that was 7.4.10. And number 4, there we go, is the same thing, only using temperatures. A simple random sample from a population with a normal distribution of 108 body temperatures has X bar of 98.4 and S equals 0.67. Construct an 80% confidence interval estimate of the standard deviation of the body temperature. Is it safe to conclude that the population standard deviation is less than 1.6? Well, if it's inside or outside the confidence interval is how you're going to answer that question, right? We're going to go through the same process that we went before. N is 108, so N minus 1, or the degrees of freedom, is 107. We're going to use 100 on the chart because we don't have the exact numbers listed there. It just goes up to 100, and that's it. We know that our standard deviation is 0.67. We're going to need that in there. And we are talking about a 90%, 80% confidence. If your confidence goes from 80 to 99%, does your confidence interval get wider or get smaller? Well, one way to think about it is the smaller confidence you have, the smaller interval you have. The wider interval comes from a higher confidence. It's because if I want to say I'm 99% sure, that means I'm pretty sure. And to be pretty sure, I better cast my net pretty wide to make sure I include all those values. Whereas if I'm only 80% sure, I think this is the range. I'm 80% sure, I can have a smaller range because I'm not totally sure about it. So smaller number, smaller interval. Larger number, larger interval. That's how that works. Anyway, so I have what I need. 80% means that I have 10% on either side of that tail, right? So it looks like this. Here, knowing what's to the right is going to be 90%. Over here, when I'm looking at what's to the right, it's going to be 0.10 or 10%. So I can find my two chi-squared values that way. Here's chi-squared left, here's chi-squared right. I'm going to find those two values, and then it says you can use, by the way, a different calculator, or you can use the table or whatever. I thought by using the table we get the same answer. I'm getting mine a little different. It could be that my calculator is rounding things a little differently. I don't know. Maybe because they're doing 2 decimal places and I'm going out 3. I'm not sure. Mine are off by a little. Hopefully in the range that would be okay. All right, so just looking at our thing here, we have 107 degrees of freedom. So again, I would just use 100. And then for the left, I had 0.90, which is here, 82.358. It could be that I'm reading these poorly. My eyesight actually 82.358. And over here on the right, it's just 10%. So I would go to the 10% and then go down to 100, 118.498. And then I could use those two numbers to plug in and get my confidence interval for this, because I know everything else. I know I have 107 as my n minus 1. I know that on the right I had 118.498, and my S was 0.67 squared. And on the left I had 82.358. Maybe I'll do one more just to see if I'm getting the same calculations. You can see the chart that I've found the right numbers if I'm reading them correctly. Anyway, second function, square root with the fraction underneath. Let's put parentheses around this 107 and then 0.67, that quantity squared, and then 118.498, and my calculator gives me 0.64. Nice, that's what they had as well. And on the right hand side, this should calculate to 0.76. We'll trust that the other answer would come out the same. So there's my two values for that. Now, on my homework, it says number 5, but I'm omitting that one because it was kind of lengthy and I didn't think you'd learn that much from doing it, so we're just skipping on to number 6, which is number 5 on your homework. So this looks like number 5. Okay. Listed below are sample speeds. What did I do with that? Ugh. I need my little cheat sheet of the chi-square table. Okay. Listed below are speeds measured by traffic on a busy highway. This simple random sample was obtained at 3:30 p.m. on a weekday. Not information we really need, I'd say, except that we're talking about 3:30. Use the sample data to construct a 90% confidence interval. Estimate the population standard deviation. The interesting thing about this is that we don't have the sample standard deviation. We have to go find it, right? And so you can click on it and do it right there in Math Excel, in Statcrunch. If you've forgotten how to do that, maybe I can pull that up really quick and do that. Number 5, click here, open in Statcrunch. This is not the same data that I have. I can't use it for this particular problem, but you could when you're doing yours. So here's our thing. We want to go to Stat, Summary Stat columns. Click on that to put that first variable because that's where our stuff is. And we want to find the mean and the variance and standard deviation and so forth. Compute. And we are talking about the standard deviation that's listed right here, 4.27 for this. We have a mean. We know that n is 12 and so forth. So we have what we need to do that problem by using Statcrunch, and that's how I would do it, but I'm going to have to do it using the calculator because I printed this off and can't access that. So if you're doing it on your calculator, you'd go to data. My data is empty, so that's good. I'm going to have to put all this data in, 65, 64, 64, 55, 64, 55, 59, 58, 59, 70, 62, and 67. That's 12 pieces of data. So I know something. N equals 12, so my degrees of freedom are 11. Now I'm going to go to second function data. Go down 1 to the stats, hit enter. I've got my data in L1, so that's blinking. I only have one of it. I would want to look at each one individually, so that's good. And I hit calculate. N is 12, as I figured. Notice they have a population standard deviation. We can't use that one. It's no point. We don't know what the population is, and we're just looking at ours. So we're interested in S, which I'm going to go out 3 places and call it 687. All right, so we have the S that we need. We know that we're talking about a 90% confidence because that was given in the problem. If I have a 90% confidence, then my 2 areas are 10%. And then if I divide both of those by 2, I'm looking at 5% on each side, or 0.05, right? So I know my degrees of freedom, and I know I have 0.05. Again, I'm going to show you this, even though I've showed it to you already. If I have 0.05 over here, then I have 0.95 over there, and that's what I'm going to use for that left value. And on the other hand, if I have 0.05 over here, that's what I use because I'm always asking what's the area to the right. So that's why I'm doing that. So I have that 0.95 and 0.05 with the degrees of freedom of 11. So here's 11, and I have 0.95, which is over here, and then I have 4.575. And then I know I need to use 11 and 0.05, which is here, 19.675 for my right-hand value. So I got those 2 values by doing that. And then I'm going to go over here and put that in. I have n minus 1, which is 11, times my standard deviation, which I said was 4.687. It will change it if you're rounding things differently. So you see how they say round to 1 decimal place? Like maybe they rounded to 1 along the way. I don't know. It's going to change things a lot if they did. I'm going to go with, we don't like usually to round things off too small to begin with. And I'm dividing by the right hand value here, and then over here the same thing on the top, but I'm dividing by my left value here. What are we finding here? We're saying that we're 90% confident that the actual standard deviation for this sample or for the population is within these two values. We're 90% confidence that our confidence interval includes the actual value. We know for sure it includes this sample standard deviation, but we're saying we're 90% positive or confident that the population standard deviation is included in our interval. So let's see what they got. Well, I know what they got. Let's see what I get for that. Second function quit always gets me out of trouble. Then I go 11 times, I don't need to do parentheses, 687. I don't know why. Sometimes I just do. And then over 19.675, enter. And I get 3.5 rounded to 1 decimal place, which is what they asked for, which is correct according to the answer I have at the bottom. And according down here, the answer to the second half is 7.3. Same thing, only you're entering a different number at the bottom. Now, the question is, does the confidence interval describe the standard deviation for all times during the week? Well, it's only at 3:30 on a weekday. So that was information that we needed to answer this one, right? The confidence interval is an estimate of the standard deviation of the population of speeds at 3:30 on a weekday, not at other times. Obviously, different times you have different speeds going on. So it's not for every time, it's for that one particular time. Now we could do a sample of some people at 3:30 and some at 5 in the afternoon and some at noon and some at 8 a.m. and some on a weekend at 2 in the afternoon. We could do a bunch and then we could look at the average of all the times, but this is just for one particular time, so it doesn't service any other purpose. Okay, that's it for 7B. You have 8A and 8B and then you're almost done. So you're doing so great. Stick with it. It's not always easy, but you can do it.